Hello, everybody. This is Dave, and today we finish up our lessons on significance testing with a test about a population mean. You should have already gone through the previous lessons on the basics of significance testing and then a significance test using a one proportion Z test. When we're taking a look at significance tests, again, I like to always use an example to explain the various processes. So let's take a look at this. A company claims to have developed a new AAA battery that lasts longer than its regular AAA battery. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. So right away, they give you a value that's going to be really important because that's an average, but it's for the entire population. So that is going to be our mu value. An SRS of 15 new batteries, all right, they tell you that it's a sample, so we already know that we're going to be getting an X bar here. Lasted an average of 33.9 hours with a standard deviation of 9.8 hours. Now that standard deviation is not the standard deviation of the population because they've listed it in the sample. You'll remember from our work on confidence intervals that if you don't have the population standard deviation, what we will do is we will estimate that with the standard deviation of the sample. Do these data give convincing evidence that the new batteries last longer on average? All right, so we always start with the same idea. State, plan, do, conclude. So if we take a look at state, again, we have H naught and we have HA, or the alternative hypothesis. Remember again that the values aren't actually what the hypotheses are. It's actually a statement of mu. Always use the population parameter when you are stating what our hypotheses are. So in this case, our null hypothesis, or the fact that there is no change, would be mu would have to be equal to 30 hours. Please use units when we have them. The alternate hypothesis, though, is we're thinking, now hold on, we have a sample with a higher average than their average. Perhaps the parameter is actually greater than 30 hours. So again, within the question, it gives you an idea of what it is that you should have as the alternate. You'll notice again that the second part, where mu is equal to the true mean lifetime of the new deluxe AAA batteries, that is the second part of the state that has to be said every time. You state the two hypotheses, and then you state the context of the problem by which mu is associated with. So from there, we go to the plan. And again, for the plan, we are going to try and carry out a significance test for mu. But in this case, we have three conditions that we have to follow, just like we did with proportions, just like we did with confidence intervals. And the first and most important always is randomization. And you're either going to have a random sampling or you're going to have a randomized experiment. The 10% condition, again, is our verification of independence, the fact that we haven't taken a sample too large with respect to the population so that we can actually maintain the independence required based on our studies of probability. The third condition is the one that's different between means and proportions, and instead of dealing with large counts, we're dealing with this idea of large sample. So if you remember back in confidence intervals, we talked about this thing called the CLT, or the central limit theorem. Now, if we have a population that is stated as normally distributed, we already know that the sampling distribution has to be normally distributed as well. But here's the best part. If we don't have a normally distributed population, but we have a sample size large enough, in this case, n has to be greater than or equal to 30, that's our favorite number, then we can still say that the sampling distribution is normal. That's the use of the CLT. So again, the CLT is not used in the case when the population already is normal, but if it's not normal, we can use the CLT so long as we have a large sample size. Do not use the CLT with proportions. It does not apply in the proportions case, at least in high school statistics. Here's the problem, and I have a lot of students that ask me this problem, and here's the answer today. If the population distribution has an unknown shape and we don't have a large enough sample size, this is a bit of a tricky thing, because now we actually have to get more evidence to support this statement of whether we can use a normal distribution to approximate our particular scenario. And so in this case, we are going to first and foremost shift to t distributions. We do that because we don't have the population standard deviation. But beyond that, what are we looking for? Well, we're looking for skew, or we're looking for outliers. This is where you got to be careful, because this isn't the land of of pre-calculus where a little bit of curve means that it's not linear and things like that. We are looking for obvious cases of skew, obvious outliers, and if those are present, we're not going to be using the t-distribution. So once we have all of this information and we've verified our particular conditions, now we move to the test statistic. This is the exact same calculation that we used when we first learned about z-scores. This is the calculation that we used when we were dealing with proportions and significance testing. In our case, though, we have two different equations to deal with. We are dealing now with the standard deviation of the sampling distribution involving the sample means. Well, that's a different equation now because we use sigma over the square root of n. Remember that if we don't have the standard deviation of the population, we are just going to use the sample standard deviation in its place. If you look at equation sheets, you'll notice that it's almost always listed as sigma because that is the case when we know what the sampling, or when we know what the standard deviation is of that population. But be very careful. You have to read the problems appropriately and get the information that you need. From there, we know that we're in t-distribution land because we're dealing with this sample. And so our test statistic in this case is going to be what's listed there. And again, you'll notice that we have substituted S sub x for sigma because now we are estimating that particular value. And so this here will give us our test statistic, but we also have to remember that when we're dealing with t-distributions, every t-distribution is dependent upon the number of degrees of freedom, which in this case is always going to be, on a conservative side, n minus 1. Now this has been a sticking point for some folks because we use technology a lot, and when we use technology a lot, what ends up happening is we get a completely different degrees of freedom. My advice to you is to understand the difference between conservative and the technological degrees of freedom. The technological degrees of freedom are an algorithm that is well beyond the scope of this course. The conservative end is just saying, okay, we are going to round down. We are going to keep it simple. We are going to make sure that our estimates are always going to be an underestimate of what potentially could be a more accurate representation. Because the thing is, if we overestimate things, and let's say for degrees of freedom, instead of using 14, we use 18, well, first and foremost, that doesn't make sense to the whole idea of conservative degrees of freedom. But beyond that, if you have now a p-value associated with this new distribution with a degrees of freedom of 18, that value could potentially be overestimating the actual p-value associated with your scenario. So when we say conservative degrees of freedom, all we mean is we aren't trying to overestimate things so that we can be more sure of the results when we have this particular distribution. So I've shown you the calculations here. You can see that the t-score here is 1.54. Again, that's based upon a standardized distribution which is centered at 0, and now we are finding the p-value that's above that because again we are using the case where we got a sample that was much larger than the stated average, so we think that it's probably higher. If you're unsure of this, recognize the fact that if you had a t-score that was negative 1.54, you could still find a tail p-value, but you'd actually be finding the lower tail p-value. So recognize the fact that these distributions are symmetric, and so because of that, even if you're not 100% sure, what you are sure of is the fact that you're always going to be finding a tail probability. All right, so we have our t-score, we have our degrees of freedom. In the bottom left there, I've given you a little snapshot of table B, and what it's showing you again is that one of the columns is the degrees of freedom, and then the upper row is giving you the p-value. Well, we know that we actually can't find the exact value using this table, and if you take a look at the values, we notice that our particular t-score is in between the values when it's 0.05 and 0.1, and therefore the best we can say is that our p-value is between 0.05 and 0.1. Now I would hope that most of you are going to use your calculators, and if you use your calculators, it will give you the exact value that you can then make a clear inference on at the end. So if we go then to a quick little statement about table B, just watch out for table B, because once you get up to a certain number of degrees of freedom, you're going to be stuck in between values. Once you get over 30, then you're kind of skipping up by tens. Just recognize that the term conservative means you're always going to round down. If you have the degrees of freedom of n minus 1 and say it's 43, you're going to round down to 40. If you have 49, you are going to round down to 40. Use that term conservative and recognize its importance here. Again, if you're using technology, this is completely not important to you. I would still recommend, though, that if you're stuck on a problem, this is always a good way to go. So if we summarize this like we did with the sample proportions, the first thing we have to recognize again is that we have this t-score. We are no longer using a z-score, we're using a t-score, because we don't know the standard deviation of the population. So that was kind of our key to use this particular score. From there, when we set up our hypotheses, we go according to the problem. So again, there's the three considerations. It's either going to be greater than, less than, or not equal to. And you'll notice the not equal to now, we're getting into a two-sided test. And so when that's the case, remember that we have to find the areas of both and then add them up. Hopefully you recognize from proportions that the areas are actually equivalent in both tails, which means if you find the area of one tail, you could simply multiply that by 2, and that gives you both areas. I would highly recommend that if you do a two-sided test, sketch out the curve and show physically that you understood it to be both areas, and then you can just simply multiply that by 2. With a conservative degrees of freedom, we simply take n and minus 1. So how does this relate to confidence intervals? Well, it relates to confidence intervals the same way that it did with proportions. If we have a significance level, let's say that is 0.05, which will be almost always the case, well, that's going to give you similar information as a confidence interval that's 95%, which is fantastic, because again, what that means is if we reject the null hypothesis, then the confidence interval shouldn't capture the true proportion of mu naught. So again, this connection between the two is essential. I've seen a lot of multiple choice type scenarios where they say, here's the significance test, what would the confidence interval do? And this is what they're looking for. So again, you'll notice the equation for confidence interval is exactly what we've seen in the past, x bar plus or minus t star times s sub x over the square root of n. You'll notice again that we're using similar quantities in both tests. So this is an important connection that we have to remember. And so if it rejects the null hypothesis, and that means it doesn't get captured by the confidence interval, then if we do a significance test and it fails to reject the null hypothesis, then that implies that, of course, the confidence interval will contain mu naught. And again, the actual area pictures of this are vital in your understanding, because if we're talking about confidence interval, we go from the center and we go standard deviations away from the center. Well, outside of that would be the tail probabilities, which means this is the connection that we're trying to see. What is a rejection of the null hypothesis? It would be within those tail probabilities, which would be outside that area defined by our test statistics. All right, so there's a specific type of test that I want to make you aware of. The next unit is all about dealing with significance tests when you have two proportions or two means. But those particular tests are based upon samplings from different populations. But what if we take another sampling from the same population and then we want to compare those two values? Well, we learned about experimental design quite a while ago, and we learned about this idea of matched pair design. Well, within matched pair design, the idea was that you give both treatments and then you compare those values. Well, this is going to result then in this concept of paired data. So the key to paired data is the fact that all the data comes from the exact same population and the values are actually compared. This is most obviously seen in an experimental setting. So when we have this, we're actually going to have to deal with a paired T procedure. Now this is exactly the same as the procedure we've just gone over, except for one additional step, which is the comparison of the two values. So let's take a look at an example here where this paired data could come into play. Let's say that there's an experiment to determine the effects of caffeine withdrawal, and we have 11 volunteers who are diagnosed as being caffeine dependent to serve as subjects. Now, the word volunteer always scares people in statistics, but remember that this is an experiment, and so we don't have to randomly get volunteers. Once we have the volunteers, we have to randomly assign the treatments that they get. That's where the randomization takes place in an experiment. So the problem with this particular question is that researchers want to know if being deprived of caffeine would lead to an increase in depression. Well, there's a lot of variables associated with that question in terms of what each individual may do as a reaction. Maybe some people get angry. Maybe some people don't have an effect. Maybe some people have been caffeine dependent for longer. Maybe they're older. Maybe their gender plays a role. So if we want to get the data then for this experiment, the best way to do this is to take each subject and then measure their level of depression when they have caffeine versus when they have a placebo and take the difference. So this is a key statement here because each subject is being measured in both cases. And so this is the signature of a matched data situation, is that each subject now has a measurement and the difference is taken as a result. You will hear questions like taking tests with sleep deprivation, and they will have, here's a person that took a test before they were sleep deprived, and here's the same person taking a test after they were sleep deprived. Here's the difference in score. What does that tell us? So this is exactly a similar case to this. Again, you'll notice that there's a difference of -1 at the bottom. That's completely fine because in the context of this scoring system, it was absolutely possible that that happened. So again, this is the signature of a classic matched pair data set. So the first question we need to ask ourselves is, why do we do this random assignment to begin with? It seems like a useless thing. We give everybody the placebo, we give everybody the caffeine. What does the order matter? Well, the fact is there could be underlying reasons why a particular person's mood has changed. Dealing with humans in an experiment is the hardest thing to do because we are very unpredictable. So things like the weather, maybe you woke up on the wrong side of the bed, maybe you didn't enjoy your morning coffee, maybe you had a rough drive to work. Whatever the case may be, there could be other reasons why that person doesn't feel good that day. So a random assignment of which treatment you get first is actually a nice way of lowering those effects on the actual study itself. So random assignment is one of the key features of any experimentation. So please make sure you remember that. And when you see questions like this, write that out explicitly, that random assignment took place. So if we start getting into our significance testing, first thing, we have to deal with state. And so in our case, we are studying whether caffeine deprivation has an effect on depression. Well, the theory then would be a null hypothesis where there is no difference. And this is implied. So that's where these paired data situations get tricky, is you have to read into that. What a lot of students do inadvertently is they put in some average value that they've calculated from the table or something like that. No, you have to read in and understand the study. So in this case, we have labeled our parameter as mu sub d, where the lowercase d stands for difference. It doesn't matter what you make your notation so long as you use mu to indicate that it is the parameter, and then any subscript you use, you're going to state in the second statement here what that actually represents in context of the problem. So make sure that you follow these clear steps every single time. So we are not given a significance level, and the rule of thumb in statistics is if you're not given a significance level specifically, you're going to use 0.05. And I would say that 95% of the problems that you're going to deal with are going to be with an alpha of 0.05. There will be cases given to you in textbook problems and maybe even college board problems where they decide to mix it up a bit and they'll give you 0.1 or 0.15 or something like that. So now that we've done that, now we get into the second part of significance testing, which is our plan. We have to check the conditions. Well, the first condition, of course, is randomization. Well, in this case, the random sampling isn't what's important because we know it's an experiment. So in this case, the random assignment of treatments is absolutely the essential element. And of course, we've listed that here. The 10% condition is in every significance testing case, but in this case, we're not sampling, so we don't actually need to check this 10% condition. This is a thing you want to put a star beside, because even though we don't have to check the 10% condition, I want you to show that you don't need to check it. Remember, in statistics, it's all about demonstration of understanding. And this is a demonstration that you get. I should check the 10% condition, but guess what? Because we're not sampling, we don't actually need to in this case. Okay, so this is, again, an important element. Where it gets tricky is when we now deal with this large sample situation. Well, we don't actually know anything about the distribution. And we have a really small sample size, which means for the first time, we are going to have to really work hard to verify our use of a normal distribution in any sort of calculations we make. So I've given you 3 different plots here. And the one that I would recommend the most to start with would be the box plot in the middle. The one on the left, that's okay, but it really doesn't tell us much. So to save time for yourself, I would first and foremost go to a box plot. Now that box plot may make people think that there's a significant skew. If you're not convinced from the box plot, then the last plot, which is the one that we kind of gloss over when we do these lessons in the course, but a normal probability plot is absolutely a great tool to use in this case. Now you'll notice again that these are sketches. Yes, they made the normal probability plot look pretty good, but you would literally just have to draw the axes and put the dots about where you see them on your graphing calculator. If you don't have a graphing calculator, then truly your only choice is probably going to be the box plot. Now, what are we looking for? Well, we're looking for 2 things. We're looking for outliers and we're looking for skew. If we take a look at the box plot, we can see that there's no outliers identified by the box plot. Well, that's fantastic. That's one of the cases. If we take a look at the skew, though, we can see that that median, the bar in the middle of the box, has shifted towards the left. That suggests that there is a potential skew. The normal probability plot indicates that there is also some skew present, but you see that signature is of a slight skew, not of a strong skew. And so based on that, we don't have outliers. We see a skew, but it's not significant in whether we would actually perform the test or not. So we feel pretty good that T procedures would be accurate. This is going to be the hardest part of significance testing with means for you, is checking this condition, not believing right away that, oh, well, the sample size is less, but the data looks pretty normal. You can't do that. You have to go to these plots. At least one of these plots, I would go with the box plot first. All right, so now that we've gotten to this point, we can go ahead and calculate the do portion. The test statistic, again, you can calculate using our equation that we know. We can find the p-value based upon that test statistic. A lot of you are going to use your graphing calculators for this. If you don't, then your conservative degrees of freedom will be equal to 10. The ones with your calculator will be quite a bit different. But based on this, you'll notice that I haven't shown a lot of work here. I highly recommend, no matter what, test statistic, show that calculation explicitly. When it comes to the p-value, if you're going to use a calculator, write down what your inputs are, be explicit about those, show where the value comes from. If you're using the table, flat out state that you're using table B, and the answer is going to be whatever it is. From there, we can now make some conclusions. So we have a p-value that is really, really small. That is quite a bit less than 0.05, so we reject the null hypothesis. You'll notice in the statements that it has used the p-value explicitly. I would go even further and actually put the inequality that that value is less than 0.05, so we reject the null hypothesis that mu sub d is equal to 0. The second statement here is what you also need at a conclusion. You don't simply compare the values, then you state what that means in context of the problem. We have convincing evidence that the true mean difference, yes, I've shown what the calculation is, in depression score is positive for subjects like this. That's all you can do. You're not the scientist in this case. You are simply the statistician taking the values, relating those into some sort of inference, and stating what that inference means in context of the problem. So, that's what a significance test looks like when dealing with means. In general, as we wrap up this chapter on significance testing, it's important to recognize how to use these tests wisely. What a lot of people think is that this means for any given test, I can just go ahead and perform the calculations because whatever setup is there must be good enough or whatever the case may be. It's important to recognize that that's not true. First and foremost, before any significance test can be used, you have to understand the experimental design of the scenario. So take a look. Are they explaining randomness? Does it sound like there's bias associated? It won't be implied. It will be explicit that there was bias. So I would pick the first 10 people that walked through the door or something like that. So it's important that when you start these significance tests, read into the problem, make sure that you feel good about the fact that all the experimental design has been done to the best of the ability so that these tests will have meaning. From there, we have to recognize the fact that if we're selecting a significance level, the smaller level that we pick, the stronger evidence is going to be needed to reject the null hypothesis. So this is an important element to remember, is that if we want strong evidence, then we're using smaller significance level. At the same time, with a smaller significance level, that means that we have higher power. Well, a higher power gives a better chance at detecting a difference if it really exists. So one of the key things about a significance test, for it to be useful, is you have to be able to detect whether a difference actually matters or not. So if you have a small sample size, it's going to be a whole lot harder to tell if there is a small difference in between the null and the alternate parameter. Whereas if you have a large sample size, you're going to have a better chance at actually detecting smaller differences as being a reason to reject the null hypothesis. So sample size plays a key role in this. You will need to explain that potentially in written form, not necessarily in calculation form, though in confidence interval calculations, we were actually figuring out the sample size requirement to get the margin of error that we need. So remember that connection may be necessary. The second thing I want to say about using tests wisely is this idea that large differences don't necessarily mean significance, and neither does small differences. So if the large sample size is available, small deviations will actually be considered significant. So with a small sample size, we may only have a small difference, but in that case, because we haven't taken a larger sample, that may not necessarily be significant. Again, you can go back to the calculation of the standard deviation of the sampling distribution itself to notice that if we have a larger sample size, that distribution will become narrower, which means that is, again, would show that tiny deviations could be a little more significant than in a different distribution. And the final statement I will state is this idea that if we have a significant result from a test, that doesn't mean that that significant result would work in other settings. Even though we have this experimental design and the weeks and months that it took to prepare for this experiment, and then we actually perform the experiment and we get these results, it doesn't necessarily mean that in another setting that the significance would also matter. It means that this significance could be used in future studies to determine whether it has validity in those particular studies as well. So, folks, that's significance testing with one proportion and one mean. You all have a great day.